Hey everyone. Today we'll be exploring Twistors, and the way I'm going to do this is first we'll start talking about one of the basic concept, that is the Pauli matrices, and then we'll move on to discuss how Pauli matrices actually help to build spin-offs, and then finally move from uh, we'll connect spin-offs to twister spaces in the Minkowski space, right? And then we'll think about some generalizations, and we'll see how to go ahead from that. Right. All right. Right. So one of the first things that you talk about is polymatrices, right? What are the polymatrices? They are just sigma one, sigma two, sigma three, coupled with the sigma naught, form the basis of the Hermitian matrices that constitute two by two Hermitian matrices. So what does it mean? So these matrices, as you will see, they give some sort of uh, operator space, or like some sort of like they transform vectors, they allow vectors to interact with other vectors and form some sort of algebra, as we'll see, right? So this comes up everywhere, especially if you're starting with quantum mechanics and all that, like yeah. So there you have sigma 1, sigma 2, sigma 3, three matrices, polymatrices, and then sigma naught is the identity matrix, 2 by 2 identity matrix, and then you have this sigma j is given by delta j3, and so this is how you will see vectors interacting with sigma matrices, right? Because through this dot product with the sigma, right? So now once we define the vector sigma as we couple it to a vector basis, that is ijk, and once we do that, we can associate like sigma, and we can treat sigma like a vector in the same vector space as any other arbitrary vector that you define, and then we can do this, right? So we can so this is an exercise. So if you take a dot sigma, right? So you end up getting a1 sigma 1 plus a sigma 2 plus a3 sigma 3, right? So now that will in the matrix. So when you compute this, it will give you a matrix corresponding to the delta. So everywhere you go, you have the component with the a vector that gets marked up, and that is how you have. So the most important relation, so why sigma matrices are super important, is because of this particular relation, right? So when you take two vectors and dot them with sigma, then they give you the natural definition of dot product and a cross product, and this comes in a pair, right? So you have a real part and a complex part. The product constitutes like the complex part, and the this thing, the dot product constitutes the real part. So you can think about how sigma matrices actually land up into this. I just identity matrix, two by two identity matrix, yeah. So then why is this important, right? So first of all, when it comes to discussion of like when it comes to talking about angular momentum and spin half particle, so you so it you need an extra you can't deal with your normal spin or angular momentum anymore, right? Like what do you think of classical mechanically, like classically, right? So you need an extra space when it, especially when spin comes into the picture. So then after that, so in order to account for this, you have the spin of in a particular direction defined, the spin operator in quantum mechanics defined using your sigma matrices, All right. So sigma z becomes your, or in this case, like, so since we have associated the vectors, with the component sigma 1, sigma 2, sigma 3, the sigma that is along z direction becomes your the spin operator along, uh, to determine the spin along z direction, right? So from here, we'll move on to, yeah, so this is what happens, right?
Um,
As I,
Pradyot, um,
yeah.
so can you scroll up a bit? Is there any relation between the geometric product that is your wedge? Well, yeah, actually your geometric product and this, because even the geometric product yields in like maybe a wedge product and a dot product both, and the wedge product here is just your cross since it's in three
Um,
dimensions.
yeah, so when you go into higher dimensions, like that is
Yeah,
more than three,
yeah,
you do have like certain interesting relations coming in with your geometric products as well. That is the wedge and the
yeah.
this thing. Yeah, so all those things. But
Mm.
more importantly, right now in three-dimensional space, this is where it's like more simply reduced to something that is just very organic, right?
Right,
The
right,
dot plus the cross. So that is where it becomes slightly important. So you have a natural definition of the dot and the cross arising from your sigma matrices.
right. Mhm.
So,
Okay.
so yeah, and so yeah, so once you write down the operator, so you have the operator, and then this is the angular momentum, this thing, the eigenvalue. So you have the operator, and then you have the eigenvalue of the eigenvalues. And so if you, yeah, so if you explicitly write it down, right, like I said, so you have your sigma z, that is basically sigma 3, the sigma matrix along the z-axis is, yeah. So once we start talking about the spin, we slowly need to define. We see that spin is something that is okay. Spin is a very complex object because you would imagine spin to be oriented along in a particular direction only, but then because of the quantum behavior, right, there are like ladder operators. That means you can actually change your spin. If your spin is oriented in the positive upwards, positive z direction, you can have a spin along other directions as well. So in order to account for this, so you obviously, so when you apply a ladder operator, there is some kind of change that happens, right? So you're now moving from like no spin along the x or y directions. You're actually trying to determine what the spin could be in those directions, right? So in order
Pradyot,
to talk about this, yeah.
uh, so you kind of in passing mentioned this thing about how you have raising operators between the spin states.
Mhm.
Could you elaborate a bit more on that actually? Because I've never heard of that before. That just sounds fascinating.
Yeah, so I'll come there, right? So,
All right.
uh, so once we start talking about like what could this supposing I measured a particle
Mm-hmm.
and I find its spin to be plus or minus h bar by 2 along a particular direction. This is a fermion, so it has
Uh,
spin half,
yeah, yeah,
right?
yeah.
Yeah, so once I measured we spin up or down along a particular direction. Now I can ask the question, what happens to the spin in the other direction? And since there is no like determined answer like after the measurement process, right? So you have just a probabilistic prediction. So that is where your spinors come into factor, right?
No, no, no.
So what?
I got that.
Yeah,
And like I'm
I'll
just gonna
come
add
there.
in a
I'll
yeah,
come
yeah.
there.
Okay, okay. But
Okay, I'll come there.
before you
Okay.
get into that, I'm just gonna add in a small aside, like just on a quantum mechanics setting. like the reason this happens is because all the spin, because you have because okay, your collection of sigma matrices, they obey the SU2 algebra, right?
Yeah.
And the way the Lie algebra defined is sigma I, sigma j. The commutator of sigma I, sigma j is epsilon ij k sigma k. So what that means is that your sigma matrices don't commute, which means that you can't find a simultaneous eigenbasis for all of them.
Yeah.
And since each of them have a different explicit basis, like that's why you can't. Like that's why, like if you measure it along one of the axes, you have no information along any of the other ones.
Yeah, and that's the same algebra you have in for the angular momentum.
Yeah, exactly. Yeah. Which is incidentally how historically we got to spin, I believe, right?
Yeah,
Like they just looked at it and they were like, oh, this looks like angular momentum algebra.
Yeah,
So let's just call it spin.
Yeah.
Anyway, yeah. Okay, continue.
So one thing to remember here, like one thing to definitely remember here is that you have fixed, in some sense, just fixed this spin along the z direction to be plus or minus half. Right? I mean, you do selectivities plus half or minus half, but you fix the spin along the z direction. Then after that, you introduce two spin-offs. So for spin up, so if it is plus half, plus h bar by 2, which is dark state, you have, or 0, you have this vertical matrix with 1 0, right? We have this column 1 0, 1 0 column that represents your positive spinner, and then you have the analog to that, which is minus, so it represents the spin minus half. And that is 0 1, right? This is a basis for your spinners that is coming in, and we'll see how exactly this plays in, right? So now, taking the other two dimensions, that is the x and the y dimensions. So once we have picked the spin along the z direction, so we consider the other two dimensions now, right? So then what you have is you have your lowering your ladder operators defined this way, right? It is not exactly your it is not exactly like along the along that particular direction, but then you need to do some sort of a rotation in order to land up with a spin along x or the y axis. So that is represented by these matrices, right? So then, so note that I have still not specified your ladder operators, whether your ladder operators is along the x or the y direction, right? So I still like need to kind of like allow for a decision about the orientation to be made, like about the direction along which I'm fixing the new spin to be made, right? Or like I'm measuring the new spin to be made, right? So that's why. So now, how do you do this, right? Is you have this s plus minus is given by sx plus minus isy. So if you see your definition of your S matrix, right? So this will, so spin along Z will be given by h bar by 2 sigma Z, and similarly spin along S X will be given by h bar by 2 sigma 1, and along Y will be given by h bar by 2 sigma 2, right? So now once I do that, but still, yeah. So once I do that, I have this coming, right? Sx plus plus minus isy is your ladder operators, right? So this sort of represents a complex spin phase that is like you're not, yeah. So it's like even though you have determined the spin along the z direction to be hit bar by 2 or up spin up, but you still have this complex phase that is coming to the picture, and that is what Sx plus or minus isy gives you, right? All right, so now once we talk about that, so we can get back Sx and Sy by this relations, right? It's a matter of simple algebra. So you just substitute and then you get back Sx and Sy in terms of the ladder operator. Note that what you have done here is in fact, right? So what you have done here is you have associated your Sx to be sigma 1 and Sy to be sigma 2, like corresponding to sigma 2. So once you have done that association, you also do something that is fixing the orientation of your bases, right? That is when you talk about the left hand or the right hand rule, right? So usually your basis is along the left hand rule, which is your X is the middle finger, Y is the index, and the Z is the thumb, right? So your usual Cartesian basis is along the left hand, is decided along the left hand thumb rule. But once you actually look at it closely, you see that there are two choices, and this is what spinners help you identify. Let me show you explicitly how, right? So yeah, so you have this relation. Now your spin now apart from the spinners along the z direction, which is this actually to be very precise, we can mention z here. But since we have fixed, if you have fixed the z direction to contain the measurement we're talking about, then we don't like, yeah, so then we don't need to specify. But then you can have your spinors in the other direction, dimension given by your these matrices, right? So if you see, there are yeah, so if you see, there are a kind of subtle play between the normal 1 0 and 0 1 basis that you have for the plus and minus in the z direction, and all this brings back your brings back the relation of the other direction with the sigma matrix, the Pauli matrices, right? So it's a little bit of like algebra that you need to do, and understanding how this comes about is a little tricky algebraically, right? So you just need a little more practice, and then you need to be able to compute stuff. That's basically it.
Yeah.
But now note that this, what does it actually mean? This actually means that you're taking your freedom of choice, the left hand thumb rule, whether to apply the left hand thumb rule or the right hand thumb rule once you have fixed C, and you're like giving this choice a space, right? So once you're giving this choice a space, so because note that you have only measured the spin along the z direction, and the rest is purely probabilistic at the moment. So which is where again the 1/√2 factor comes in, because it's half probability. So whether it's is it spin? So if you, the question is, if will you measure spin along the x direction to be up or down, and then you have two states, right? So you have a probability factor 1/√2 coming in here, and then similarly along the y uh, axis, right? So now, once you describe all this in a very probabilistic picture, right? So what we're doing here is we are really, if you look at it closely, there is more than 360 degrees or 2 pi degree of freedom to your space of rotation, right? So you need to account for this uh, double space of rotation, which is basically corresponding to your left hand and the right hand rules, right? So once you do that, so let's look at this. Okay, so keynotes. So SZ is fixed, and then you have S plus minus the lateral operator is defined on X and Y such that you have this particular relation. So you choose your x to be corresponding to the sigma 1 and y to correspond to sigma 2, right? So after you choose this, then you have this dual space, and you have the freedom of choice to use the right hand thumb rule or the left hand thumb rule for the orientation of x and y. So now what you do is, once you sort out the algebra of all this, you will see that your spin positive, okay, is connect has like four states, four possible states in the phase space. That is positive x and negative x up, x down, y up, and y down. So you have this four state, and what spin-offs, and each state is represented by one spin-off. So in the sense, instead of decomposing your like instead of decomposing this vector space in the normal way, when you talk about like two vectors, you have four spin-offs instead. So in that sense, you yeah. So that's where like your geometric simplicity, like your when you're doing algebra with more and more complex object, it becomes extremely crucial for you to be able to break down your vectors or into spinors, or you should be able to talk about those new quantities or new objects in terms of just spinors, right? So now once you yeah, so and another thing is a slight note here, because whenever you talk about spinors, you have to mention that spinors can be defined only with even dimensions. Now, what happens here is, in this particular case, is you're already fixed, since you're already fixing your
Z.
spin along z axis. So you have like you just like squish your whole like observation plane or observation sample to just two dimension, that is your x and y. So then so you're basically fixing z, and then you're projecting everything on the x and y plane. So that's what you do. And yeah, so even though we are talking about three-dimensional vectors and all that, you should note that like the z direction, just like the dimension, just gets removed out of the picture, and then you have only the interplay between two dimensions, right? Like any questions so far? And
Mm.
like with
I think you're gonna get to the part of like even graded subalgebras. Gonna talk about that later. So yeah.
Yeah, so that's basically it, right? So once you have your so your vector space is so your vector space is uh, now you have two vectors,
Yeah.
and you break it down into each. So like I've done, right? So you have two spinors associated with each dimension.
Yeah.
So in a particular set.
Yeah.
So then you have like, so that's where you have this even graded subalgebra coming in, because you can represent this notion of two vectors by four equivalent spinors.
Yeah.
So
Yeah.
yeah, okay. Also, I need to remove this, I think. Right. Anyways, so now moving on to a more geometric picture as to what spinors are and how do they deal with. So this geometric picture will actually help us later on in understanding the twistors as well. So what you do is, so you have your space of your x and y coordinates, and then you can interpret that if you have a vector x plus iy defined, you can break down the vector into two components, like into having two kind of possible orientation corresponding to the left hand rule or the right hand rule, right? So that is, if you have the red arrow that is positive pointing along the vector, then you have the left hand rule, and if you have the negative half arrow or the broken arrow, that is you have the right hand rule. Again, this is a more geometric picture, and it is made to be intuitive more than being rigorous or anything per se. So now what you see is the space slowly decomposes into two circles, or like two you know so this two two areas with like I mean not area, two into two pi uh, like degree of like a rotational space in order to get back to the same orientation. So you can account for this. So you have a space for your plus to switch to down to minus, and vice versa, right? So you have this kind of like the infinity loop or the Mobius strip coming into the picture. And once you track the orientation, you actually kind of have to give not just 360 degrees, but in fact 720 degrees to account for this space within the vector, so to speak, within just the mere rotation. So which has to be strongly do with the left hand and the right hand rules. Now coming back, uh, once we have a brief picture, a geometric picture of what a spinner looks like, and an algebraic picture as well. Now we have the whale spinners, which is these are just vectors, like unit vectors along the a is just an index for the coordinates. So you have cyclic indices, that is for vectors. So now to talk about whale spinners, this is in the Minkowski space, which has four indices or four which has four indices. So each one of it's cyclic, right? So when I talk about 2a plus 1, that actually means so if a is 1, then a 2a plus 1. So you move along the circle, right? So yeah. So now given that what we so given we define our wave Pinos pi a to be 1 by root 2 e to a plus I e to a plus 1, that is the same as this essentially. So you have this, right? So these represent the spinor the vectors for these represent the spinors for can we pause for a second? Rahul.
Yeah.
Yeah. 1 second.
We can pause it here, right? Or
All right. All right. So we define the wave spinors. This is just a notational. This is just a different notation of representing the same kind of spinors with respect to the ladder operators that we saw earlier, just a minute ago. So pi A is your wave spinor where your A index or the A index is fixed, and then you have corresponding to that E to A plus I E to A plus one. So these are your ladder operators, the basis for the ladder operators coming in. So so you have these so, this is just the restatement of how we defined the spinors originally. But these wave spinors are used to define massless fermions, and so it becomes so this and not only in 3 dimension but also in like higher dimension. So this notation becomes useful to learn. Associated with the spinor, you have the conjugate of the spinor as given, and then also once you understand what wave spinor is, um, now we slowly start talking about the twister, right? That is getting into the topic that, like, just touching the topic that we wanted to explore today. So now, how are twisters constructed? So twisters are basically constructed with two spinners, right? So instead of having so you have like a space where you have two different spinners coming in with the same dimensionality. So here A becomes, so for example, if A is two indices, and then, like, A fixes the two in 4 dimensions, right? Or in 4 dimensions, if A fixes two indices based on the way the formalism given just here. So the pi A, which is the other spinor, fixes the other two indices. So A is, yeah. So I mean, A is actually one index, but it fixes or it talks about the other two, the vector plane that is orthogonal to that particular index, right? So that is, so you have two corresponding like two orthogonal planes that are that you're essentially talking about when
So what you're saying is that you just put two spinners together and you get a twister?
yeah.
Also, what is, and okay, you have two orthogonal planes itself. For example, like one of the spinors can give you a z plus, and the other one gives you something of an x or an x minus. Can you guys hear me?
Yeah.
Gives an x or an x minus. So the plane orthogonal to that. So is that what you're saying?
Yeah.
Okay.
This leads to my very next question, which is that
Sorry.
so the Dirac spinner, the object solves the Dirac equation, is the spinner. Because effectively you're embedding two spinners within one object.
Okay.
So what's
So
the
then
difference between Dirac spinor and twistor?
Yeah,
So,
that's kind of what figure out. Either this definition kind of hints at that. It's either that or really don't understand this definition of a twister. So this part is just, I don't know.
See, I think it has to do with the space that you're defining the spinors in.
Okay.
So in the sense, this is the master, right? So once you coming in, you always have a different sort of like further different.
No, I mean,
but essentially, answering your question, essentially, like built to support massless uh, so, so
Wait, I'm just
what
add one more thing though. So you said that Minkowski define massless particle, right? That's basic. Okay. So you take the Dirac equation, set mass equals to 0. You get the exact same thing. This is defining a massless particle living in a Minkowski spacetime.
I'll come down to, and then you can see like how it connects, right? Whether it answers your question or not. So one thing is four-dimensional. So this is this these twisters represent like occupy. You can give define these twisters by the coordinates z alpha, right? So for every for a twister, you can define a complex conjugate as well. As below, right? So notice that your formalism gets slightly trickier, and you need to keep a lot more track on your plus and minus signs when you're dealing with uh, relations or idea is to orthogonal. I don't know if it just makes if it's like essentially you have two orthogonal spinors coming in, two different spinors that constitute a four-dimensional space coming in, and you define so Z alpha and the conjugate give you this relation, and this expression always remain invariant. So we will touch upon this in the next session, where I'll talk about conformal invariance is, and once we get into that aspect of things, we'll touch upon the relation. But essentially, what to introduce the idea of twistors, one this relation remains invariant throughout your twistor transformation. And second thing that remains invariant is defined like that. Note that this form is defined in this is a three form. So even though you have a four-dimensional space time, and you have a three form that describes your uh, four-dimensional space, right? So yeah, so this will have a lot of interesting algebraic uh, connotations that we will look into later. But
yeah, I guess on the next call, we can slightly go into how the twistor is essentially, as you just said, it's a projective space. Like twistor theory is on a projective space, and while your Dirac spinors
exactly.
aren't really projective.
Yeah.
And maybe highlight the difference to make it clear, because both seem like two spinor formalisms. Yeah.
Just to give you, this is another geometric picture. Just to give you some sort of uh, intuition into understanding. So, like we define spinors, then we have to orthogonal spinors coming in, and a space of these two spinors, like obviously, so these two are contained within the brackets, right? So whenever you talk about twistors, these two are contained within the bracket, and these represent the individual spinor, right? So just to give you some sort of a geometrical idea. So now what happens is so there's something called as the twistor correspondence, which gives you the relation between the two, the force twister, uh, the components of the twistors, right? So your Z naught, so this is the central, uh, yeah, so this is the correct. Once you look at it, can you guess what this looks like? Can you make something based on also your X, Y, Z are the normal Cartesian directions, and then your time is the time axis, and then c is the speed of light as usual. So Shani, like, can you see something familiar here?
What are you looking for? Like they seem like still whale spinners. So
No. This is kind of like how you begin the entire factorization process for spinor helicities, I think. Because you kind
or are
of
you
look at
talking about how it looks like the Minkowski space, all of that?
Yeah, exactly. So, right. So, what we're doing is we're talking about something that is propagating along the z direction,
Right.
and your yeah. So your x plus iy. So these correspond to the spin-offs.
Okay.
And then you have this as an orthogonal spinor, right? Note that none of these are complex, but we could very well like exchange these two and put them in the other, switch the diagonal by, but the this diagonal has like the complex elements, right? So we could do some sort of like algebraic manipulation, but essentially essentially it is a propagator that is traveling around the z direction, and you have your phase space in the x and y as well. Like you have one set of spinors defined along x and y, and other set of spinors defined along t and z, right? So that is what, and then you have this beautiful relation between the components of the twister to the this particular matrix. So this actually is the solution to the following differential equation. Which is basically traveling traveling along the speed of light.
Isn't that the Klein-Gordon equation? A massless Klein-Gordon equation?
Yeah. Exactly. Not the Klein-Gordon. Yeah.
It is the Laplacian of phi, or rather the D'Alembert of phi, not Laplacian. Sorry.
So now, where do you derive define this equation from? Is like you initially set up this question, right? You set up this question as f is equal to the contour integral with this is your complex projective space of one. So your gamma, the contour belongs to the complex projective space of one. So you have a singularity, and you're trying to essentially remove that singularity, and yeah, so with some functions, right? So the integral of some function with a singularity.
Okay.
And you're essentially trying to remove the singularity using contour integration, like removing the yeah, you're doing contour integrating over around the singularity, right? So that is where so this uh, uh, this particular contour integral, the solution to that lies in this, which is very similar to the Klein-Gordon equation. And now, so what you do is we try to look at like interesting geometric subsets of this whole thing, right? So what we do, so yeah, so this is a family solution, 2,2 variant, and thus it also possesses conformal invariance. So C1, 3 of a compactified Minkowski space. So in the sense, what you're doing is, if you have the Minkowski space, which is represented by your light cone. So now notice at the present. So what you're doing is you're moving this. So you're compactifying this Minkowski space to make it look like something like this. So we'll go into details later. So you have this point get expanded to and then there is this all the inversion that happened, right? The conformal mapping that happened. So this conformal mapping, it has to it plays a key role in trying to solve this. Yeah, so that we have your Twistor corresponding coming in, and this is so the relation, the intricate relation between as to how you go ahead trying to solve this particular conformal integral is something that we will look into next podcast, and also twistors are generalized killing conformal killing vectors and those things. So yeah, I think this should be a good place to take a pause for today.
Yeah, yeah.